So because it's becoming more positive over time, it must be going forward. Because it's going less positive over time, it must be backwards. Okay, there's another way to do this too, though. Okay, there's another way to think about this as well. So rather than just thinking about the straight numbers, we can think of it in a slightly different light. What did we say slope represented? Gavin, what does slope represent?
Just the position over time.
Which is? What's the name for that? You're exactly right. What's it called?
Velocity.
Bingo! I love it. Notice that the slope, the velocity, the slope is positive. So we would have a positive velocity. That tells us forward. Positive velocity is always forward. Okay? This is sloped down. Again, the slope is velocity, but this is a negative velocity. And that tells me backwards. Negative velocity is backwards, positive velocity is forwards. Okay? So, two different ways to look at that. Both are correct. You can either think about the numbers being more positive or less positive. You can also think about the slope being positive or negative. Perfect. Okay, number 2. We found out in the lab that the slope of displacement gives velocity. We just talked about that. Used the concept of slope to explain why this object is speeding up. So this is what our graphs looked like in the lab you guys just turned in last class. So you finished last class. Okay? This is what the slope looked like. How do we know from this slope that it's speeding up? Again, take 10 seconds, think of an answer. How do we know that this object's speeding up? Just by looking at it. Yeah, get it.
Point that it started at is like the one that's like where it's at now is like higher than where it was.
Yes, and we're talking about slopes, right? And we said slope is velocity. So notice that the slopes become steeper. So a steeper slope equals more velocity. If you have more velocity, that means you're speeding up. So you get a steeper slope and you get more velocity. I got 6 of them. Yep.
And then when you 8 in each classroom, you got room for 2 more then?
I do not. I say six should be fine for me. Just because otherwise they just get too claustrophobic.
All right. Sorry about it. Thank you.
No, you're fine. No worries. Thanks, guys. Okay. Let's look at this one then. I want you to draw a graph of the object that is moving forward and slowing down. Now, unless you have pencil or you are 100% certain, just draw one off to the side and sketch what you think it is. I want you to take 10 seconds and sketch what you think it is. Okay? And then we'll talk about it. Okay. Someone tell me what you think it is. What are we feeling? McKinley.
Like an upside down view.
So like this?
Yeah.
I love it. Okay? Anyone got anything different? Everyone likes that? No one feeling bold? Okay. Gosh, I'm so glad you said that. This is not it, but this is what most people think it is. So that's why I'm really glad you said that, because this is what I wanted to talk about. Let's talk about why it's not this one. So this is definitely going down. But remember, what does the direction mean? Going down means backwards. Going down means backwards. And notice what happens to the slope. See how the slope gets steeper? This here is this one, but backwards. It's this one, but backwards. So, this is really easy to do. It's really easy to do because that's what we think of. We think of going down as getting smaller. But remember, this is showing the position. So we're just going backwards in position. Doesn't mean we're going backwards or slowing down in speed. So let's try another one. What else might it be? So we're going forward and slowing down. I'll give you a hint. It's got to go up. But how is it going to go up? Go ahead.
It's like the example, or number 2 below it.
What do you mean below it?
Directly below. Question 4.
Oh, this one?
Yeah.
I love it. Yes. This is the one here. So, Cole, tell me why you think it's that one. You are right. It is that one.
It's that one because the one above it is speeding up as it goes.
Right. So the slopes are getting steeper.
And this slope is starting off steep and then not increasing as much.
Yes.
Slowing down.
Correct. Notice what happens to the slopes. The slopes get less. The slopes get less. So, when we're talking about these position graphs, again, remember this. This is super important. Slope equals velocity. That's just something you have to know. The slope equals velocity. For these graphs, I'm going to give you another graph where slope doesn't equal velocity. But we'll get there. Right now, slope is velocity. For all these graphs we did. Okay? Slope is velocity. So if you want to show going faster, you need to show it getting steeper. And if you want to show it getting slower, you need to show it getting flatter. Okay? So again, the explanation here, steeper slope meant more velocity, so that means a flatter slope means less velocity. Okay, so good, so good. Okay, I want you guys to take some time to do number 4. I want you to try number 4 on your own. Now, some of these we've looked at already, right? We looked at this one. We've looked at this one already. So some of these, we've talked about this a little bit. So some of these might come kind of quickly and easily to you. But I want you to put these two things together. I want you to tell me, is it going forwards or backwards? And I want you to tell me, is it speeding up, slowing down, or is it at a constant speed? Those are always going to be the things I'm going to ask you. I'm going to ask you those two things. Speeding up, slowing down, forwards or backwards. Okay, so take a minute. We'll pause here. Take a minute and see if you can answer those for those 4. So we talked about this one already. That was up here. We said it was backwards. Okay, so we talked about that part already. Zara, is that speeding up, slowing down, or constant speed? Nice. It is, because notice the slope stays the same. So even though it goes back, the slope is the same, so it's constant. Okay. We talked about this one already. Okay, we said this is going up on the position, so it's forwards. And it's getting flatter, so we said that would be slowing down. We talked about this one already too. We said it's going, again, it's getting lower on the position, so it's going backwards. And we said this one is speeding up because the slope is becoming steeper. So we're getting more velocity. Again, the fact that it's more negative is fine. All right. So what about this one? All right. Nick Vale, tell me what you got for this one, forwards or backwards? Why do you think forwards? Okay, why do you think backwards? Yeah, because the graph's going down. You're exactly right. Nice recovery. I love it. Yes, this is going backwards. And again, the reason it's going backwards is because it's going down on the graph as opposed to going up on the graph. Okay? Perfect. And Nick Eldridge, what about what's it doing? Speeding up, slowing down, or constant? Slowing down, how do you know? You just know. Feels good. Feels right. You're right. It is slowing down because you said it's decreasing. What is decreasing? Slope. Yes, the slope is decreasing, which means it's getting slower. Okay, whether it goes up or goes down, slowing down gets flat. Whether it goes forward or backwards, speeding up gets steep. So speeding up gets steep, whether it's up or down. Slowing down gets flat, whether it's up or down. Doesn't matter. Okay? All right, perfect. Questions on the front page? We're tearing it up. Okay, go to the back page. Okay, graph of the motion of a tram at the airport is shown below. What is the tram's velocity? Okay, so here's how I go about doing that. So we know the equation for velocity is displacement over time. So what I do is I figure out what is the displacement, in other words, what's the position change in some amount of time. So I'm going to start here. And I'm going to go to another spot where it intersects the grid lines. Okay, so I'm going to go to here. There's other places it intercepts the grid lines, but I'm picking that spot. So my displacement is how far does it go in position? So it goes 1, 2, 3, 4, 5, 6 forward in 1, 2 seconds. So the displacement, the position change, is 6. The time change was from 1 to 3 seconds, so 2 seconds forward, which means my velocity is 3. That easy. That's all you got to do. That's all you got to do. All right, let's look at 6. I'm going to start you, and then you guys are going to try them and see what you can do with it. All right, number 6. Consider the motion maps of the cars below. Note the motion of all 3 cars occurs over this course of 5 meters. Each dot represents the car's position 1 second later. So this is kind of confusing just because I suck at Microsoft Word. But from here to here is 5 meters. And from here to here is 5 meters. I know the scales are not the same, but they're both 5 meters. Same with this one down here. Okay, so those are 5 meters. Also, every dot is 1 second. So this is 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7, 8, 9. This one is 1, 2, 3, 4, 5, 6. Okay, so on and so forth. Same with this one here. 1, 2, 3, 4, 5, 6, 7. So just because the dot numbers are different doesn't mean they're going different. That sometimes confuses people. They're going the same distance. They're always going 5 meters. Okay, no matter what, always going 5 meters. I want you to compare and contrast the motion of the cars. Basically, tell me what's different and what's the same. Are there anything between these cars that are the same? Are there anything that's different? Think about direction. Think about type of motion, speeding up, slowing down, that kind of stuff. Constant. Think about that. B, what's happening to car 3? Car 3 map looks different than the other two. So what's different about car 3? C, assume that the velocity of each of the cars is positive. What's their acceleration? Tell me positive, negative, or 0. This is different than what we've done. I've been telling you speed up, slow down, or constant. I want you to tell me positive, negative, or 0. And then lastly, I want you to sketch the graph of each of these cars. What will each of these cars' graph looks like? Okay? Go ahead and take some time. I'm going to pause here. Take some time to answer these on your own. Again, if you don't have pencil, do it off to the side. Do it off to the side if you're not sure. But I want you to try them, see what you can come up with. What are some differences? What are some similarities? Let's focus on differences. What are some things that are different about these cars? Miranda, what's something different about these cars? Okay, good. So the speeds are different. You're exactly right. So they got different speeds. We'll stick with velocities. Good. That's a good one. What else is different here? Say again? No, what's something else that's different? What about the car?
It's a different car.
True. Jacob, what else is different?
R1 seems to be good.
Well, we had that with the velocities. I'm thinking specifically, what is car 3 doing? Hey, yes. So we have different velocities, and car 3 is slowing down. Which, by the way, that's what B is, right? What is happening to car 3? Car 3 is slowing down. And you can tell because notice that these are the same distance apart. So every second you go the same amount of displacement, which means your velocity is constant. Same here. But this one is not like that. We have a large gap, medium gap, medium gap, medium gap, smaller gap, small gap. So we notice that they get closer together over time, which means that it's slowing down. You're going less distance in the same amount of time. Okay, here we get to the tricksy one. So assume that the velocity of each car is positive. What is their acceleration? I'm not looking for what the car is doing. I'm looking for the direction of the acceleration. And your options are positive, negative, or 0. Okay. Let's start with car 1. Evangeline, what do you think? Car 1, what do you think the acceleration is? Positive, negative, or 0? Try again. Yes, it's 0. Because it's constant. See how it's the same the whole time? So the value for the change would be 0. So this first one is 0. Excellent. Okay. Ian, what about car 2? What do you think its acceleration is? Positive, negative, or 0? Try again. Try again. Nice job. Good. It's 0, and here's how I know. Here's how I know for car 2. See how they're the same distance apart. Because they're the same distance apart, there's no change. And if there's no change, there's no acceleration. So if the acceleration is constant, or if the velocity is constant, then the acceleration is 0. All right. Let's look at one more here. So car 3. Macy, what do you think the acceleration of car 3 is? Positive, negative, or 0? It is negative. Excellent. And the reason it's negative is because it's changing opposite of what's being done. It's going forwards, but it's losing its forwardness, if that makes sense. I'm becoming less forward in my motion, and I'm getting closer to 0. That means the change needs to be backwards. So I'm losing velocity from what I was doing. My numbers are getting smaller, which means my acceleration is opposite, and since I was going forward, the acceleration would be negative. Great. I'm loving it. Okay, so let's look at the shape of the graphs. Let's see if we can see what these would look like. All right, sketch the motion of each of these cars. Let's start, Trent, let's start with you. What would car 1 look like?
Would it just be like a pretty upside down U?
So why do you think?
Because that should be constant.
So constant, and you're right. Constant, though, is straight lines. So you're exactly right of what it's doing, but we would want to draw a straight line going up. So something like this. So that'd be car 1. Okay? Baldy, what about car 2? What do you think that graph is going to look like? Straight line? Going up or going down? Good. Is it exactly the same as this one? Or would it look different than car 1? I'll give you a hint. It'll look a little different than car 1. So how might it look different than car 1? Any ideas? How would I make car 2? Because it should be a little different. Miranda, what do you think?
Wouldn't it be like lower?
You would think it would be lower?
Why? Yeah.
Why?
Because
It's actually the other way around. It's faster, but you're thinking about it the right way. See how it takes more time to go 5 meters? That means it's slower. The distance between each second is less. That means it's slower. Car 1 is slower than 2. But you're thinking about it the exact right way, which is one car is faster than the other, and the slower car should be less slow. Since car 2 is going the same distance in less time, so if we were going to calculate the velocities, this would be 5 over 9. This would be 5 over 6. So this number would be bigger. Because of that, I should have a steeper slope. So they're both straight lines. They're both going up, but car 2 should have a steeper slope than car 1. That's how it should look different. Okay? Excellent. Let's look at car 3. How would car 3 work? What would car 3 look like for this one? Shane, what do you think? What do you think car 3 looks like? Okay? Am I going up or down? Why down? Okay, it's going up. And then am I getting flatter or am I getting steeper? Try again. Flatter. Yes, nice job. Here's why I'm getting flatter. Because I'm slowing down. See how they're getting closer together? so I'm going less distance in the same amount of time, so I'm going slower, and velocity shows the slope, so it's getting flatter over time. Awesome. Terrific. Stupendous. Okay, go ahead and put that one off to the side. Let's